Hey, good afternoon, everyone. Again, this is our lecture 38 in high-dimensional probability, and data science. And it's Friday. If you're offline or online, if you have your tea with you, we'll drink it together, and then we'll begin math. Good. So we stated last class. We stated the uniform law of large numbers that will allow us to compute multiple statistics from the same sample. And then, in the machine learning context, to choose the best possible hypotheses. So we would like to test multiple hypotheses from the same sample without resampling. And that's what uniform law of large numbers allows us to do. The setup is that we have X, a random variable or a random vector, maybe, taking values somewhere in some set. Could be real value, it could be random vector. And then we have access to a sample, or training data, if you like. The IID, let me write it this way, IID copies of X, meaning that they come from the same distribution as X and are independent. Then the usual law of large numbers says that whatever function we take, if we take average over the sample like this, for large n, it will be close to the true expectation. So this is the true mean, and this is the sample mean or the empirical mean of f of x. Clear, right? F of xi will become random variables too. They're independent. If we average them, the law of large numbers says exactly this, that the sample averages will be close to the true averages. Good. We would like to make that fact uniform over many functions f, in particular for the functions f that could be chosen adaptively, could be chosen depending on the data. That's what usual law of large numbers does not allow us to do. So we would like to look at the data, then decide what statistics we would like to check, and then check that statistics. So f will become kind of dependent on the data. This is a context outside the classical scope. And that is what uniform law of large numbers is saying, that we can actually do this. It says that for any class f of Boolean functions, for simplicity, Boolean means that they take values 0 or 1. If the VC dimension of f is finite, and if you forget what VC dimension is, you can think of this as a number of parameters that the number of parameters to parameterize functions in f. Okay, so if there are, let's say, polynomials of degree 11, then VC dimension will probably be something like 11. Okay, so for any class of Boolean functions with finite VC dimension, let's call it dimension D, we can uniformly bound the error like this. So this is an error, it's supposed to be small. Then we take the worst possible over the entire class like this, and on average it is finite. It is important here that the supremum is inside the expectation as opposed to outside. So this means that with high probability or on average, we have this bound simultaneously for all f from the same sample. Got to say, Now that of course will be fine because f is Boolean, right? What do we say? It will be less than something small. Specifically, the error 1 over root n, that's coming just from this, the variance. That's the same errors in the law of large numbers. But what we pay is this d log n, where d is the VC dimension. And c is an absolute constant. Okay, so the goal of this class is to prove this theorem. And then we'll apply it to machine learning, to statistical machine learning. Any questions about it? Okay, good. So the proof of this result, an important result, is based on a new tool for you. It's a very nice, very cute, nice tool that is flexible and you can apply it everywhere else. It's fun. I know you like it. And the tool is called symmetrization. Symmetrization. Symmetrization allows us, it's a very general tool that allows us almost miraculously to replace unknown distributions of random variables by Bernoulli distributions, like plus or minus ones. And here is how it works. Symmetrization lemma. This is due to Genet and Zinn. I can't remember when, the 80s, 90s. We have, let's say we have this independent random variables, IID. Actually, just independent probably. Independent random variables. And then we'll have the signs. To flip the signs, we will use independent plus or minus one random variables with probability 1/2 each. So we have n coins, and then we flip them and decide whether it's plus or minus one each of them. Then, so suppose you want to bound the sum of independent random variables that have mean zero. So I subtract the means just to make it mean zero situation. It is bounded by up to factor 2 by the sum where you just flip the signs, epsilon I, xi, just like this, instead of subtracting the expected value. Any questions about the setup of this lemma? Good. On the left, the expectation is with respect to xi's. On the right, the expectation is with respect to both xi's and the flips of signs. Okay, let's prove it. The proof is very instructive and very simple, actually, but cute. Okay, let's do it. Let's see. So first, we will write this. We'll separate the expectation. Xi minus expected value of the sum. I'm just taking expectations out. Nothing happened yet. But here's a neat trick. I will replace this thing inside here by an independent copy of xi. So I will write this as sum minus expected value of xi prime instead of xi, where xi prime is an independent copy of xi. It's kind of a ghost data. Think of, or maybe you can take another sample from the same distribution, call this xi prime. And if you average over xi versus average over xi prime, it's the same thing. They have the same distribution, so expected value is got to be the same. To make it clear which random variables I take expectation with respect to, let's start indicating this. So this is, here we indicated with x that I take the expectation with respect to xi's. And here is I take expectation with respect to x prime. And here I take expectation with respect to x. This superscription do not mean, I'm not doing it. It's just an indication, just information about what randomness is involved where. Okay, let's go on. When we take the expected value with respect to x prime, this thing looks like constant to that. So I can move expectation value with respect to xi prime up front. If you are familiar with the concept of conditional expectation, that's what we are doing. Expected value xi prime is a conditional expectation given xi's. So this xi's act as deterministic with respect to xi prime. So I move it up front. Now I'm averaging here. Good. Okay, now I'm claiming that we can move the expected value through the absolute value, outside the absolute value. Why? Why can we do this? It's a general fact. Why would be true that?
Because exactly. Modulo is.
Yeah, exactly. Yeah, this is just Jensen's inequality. Jensen's inequality for the function that's absolute value of x, which is convex. So expected value of f of x is less than f of expected value of x. The other way around, I guess. Forget which direction Jensen's goes to, but this is the correct direction. Okay, so we move it out. Perfect. Okay, now another neat trick. xi minus xi prime. Let's think. These random variables are symmetric in the sense that xi minus xi prime has the same distribution as xi prime minus xi, right? Because it's just a name, not equality in values, but distribution is the same. Agreed? Because they're identical copies. It's just up to relabeling. The distributions are the same. So in particular, if we flip the sign in front of this random variable, if I flip the sign arbitrarily, I will not change the distribution. Agreed? In particular, I can take a coin, flip a coin, and let the sign be the random, depending on the outcome of the coin. So what we can write is that in distribution, it's the same as epsilon I, xi minus xi prime by symmetry. Yeah. Agree? Everything is okay now? So far, so good? Guys, ask me if you have any concerns. Okay, we're almost there. We flipped the coins already, so we flipped the signs. So let's just rewrite this mess. And there's x sum. Sum epsilon I xi minus xi prime. And this happens for any flip of coins, in particular for the random flip of coins. And in particular, I can average. I can take expected value with respect to this flip of coins outside. Because the distribution actually doesn't change. The distribution stays the same for whatever signs I choose. So I can average, and that's of course the same. So this is a lot of expectations here. So let me just call this expected value. Now we forget what we take the expected value of. Okay, so we have expected value of, and then let's separate the terms. Just like this. And then use triangle inequality. Triangle inequality to separate the terms. So this is less than expected value of epsilon I xi plus expected value epsilon I xi prime. But these terms have the same distribution. Because xi prime is just a copy. So this is just twice expected value of this. That's it. Done. Good. Any questions about it? Good. This lemma is useful in the following context. When we have an unknown distribution, possibly a very complicated distribution, we don't know anything about it. What we can do is we can use this lemma, then condition on xi's, which means that we fix xi's now, and leave the randomness only with the signs. So now xi's are fixed coefficients. Think of them as just fixed numbers, deterministic numbers, and epsilon i's are just Bernoulli plus or minus one symmetric Bernoulli random variables. And we know a lot about them, so we can just apply Hoeffding's inequality, whatever. It's a very simple distribution to work with, completely known. So this is how we can reduce the problem about unknown distributions, very complicated ones, to the very, very simple distributions, plus or minus ones. And we will illustrate this in the proof of uniform law of large numbers. But this lemma is very general, and I'm glad you know it now. So feel free to use it. Perfect. Okay. So now next thing we'll prove the uniform law of large numbers, unless you have questions about this lemma. Good. Okay. So we'll prove this. We would like to uniformly bound this deviation. Okay, I'm just rewriting it here. So expected value. This is what we want to bound. And excuse me, f of xi minus expected value of f of x. That's what we need to bound. To apply symmetrization lemma, right here, let's to prepare to apply symmetrization lemma, let's take 1 over n outside, because there's no 1 over n in symmetrization. Let's also move the expected values inside, so f of xi minus expected value of xi. Right? Expected value of f of x, it's the same as expected value of f of xi, obviously, because xi has the same distribution, and so I can just combine them together. Okay. Now we apply symmetrization lemma. unfortunately, there is a supremum in our way. But let's for a moment, okay, don't just maybe write this yet. Just for a moment, let's forget about the supremum. Let's imagine that there is no such thing here. And then apply symmetrization lemma. It will give us, symmetrization lemma will be applied to this instead of xi, to f of xi instead of xi. So this will, symmetrization lemma will then give us 2 over n, expected value of epsilon I, f of xi. Symmetrization. That is if there is no supremum. Okay, agreed? That's just a direct application symmetrization lemma. Okay. Now, you got to believe me when I say that if you have the supremum, you can still run this argument. You can still have the symmetrization lemma even with the supremum. And that's going to be the, there's no homework yet anymore, but let's say this is an exercise. Exercises to prove this a little bit more complicated version of symmetrization lemma with the supremum. But you can trust me that all these little steps they go through. The proof is very flexible, and it actually, the key point is that the expectation can be taken outside the supremum as well. The one key point was that expected value can be taken outside the absolute value because absolute value is convex and Jensen's inequality applies. But we will also have to take expected value through the supremum. And that is also true. The supremum is kind of maximum function is kind of convex. So you're going to check that. Okay, good. This expression, by the way, this expression is called, in statistical machine learning, is called Rademacher complexity. It's an accepted term of f. Okay, let's keep working with this Rademacher complexity. Like I said, the symmetrization lemma is good because it allows us to now condition on xi's. So we'll treat these as fixed now and leave the randomness only with the flips of the signs with epsilon i's. So let's write this carefully. Condition on the random variables xi. We treat them as fixed numbers, thus leaving the randomness with epsilon i's, the signs. The only randomness now remains in the signs. For any f, what do we see? It's a sum of plus or minus some numbers. It's like plus or minus ai's. Can we bound it? Sure. Höfding's inequality, that's our first concentration inequality, allows us to do this. So we'll apply Höfding's inequality. I think lecture 9 is where it is. Höfding's inequality, possibly for lecture 9. And it tells us this. Epsilon I, f of xi is greater than t, and let's call this ai's. It says that the tail is Gaussian. So it's minus t squared, but in this situation, because there is 1 over n factor, we can move it to here, to the right-hand side. And the right-hand side becomes nt, not t, right? So it will be e to the minus nt squared divided by the sum of the coefficients squared, ai squared. That's Höfding's inequality. E to the minus t squared divided by 2 twice. It's like Gaussian tail. E minus t squared over sigma squared. That's 2 sigma squared. That's Gaussian tail. So that's Höfding's inequality. Each of these numbers, AIs, each of these numbers, it's a Boolean function, so it's in 0, 1. So the sum of the numbers is the sum of these numbers is at most n. Each AI is either 0 or 1. Okay, great. We got a great bound. Can't be happier. N t squared over 2. What makes us happy here is n. Okay, so what have we achieved now? We would like to bound this thing for each f, for each fixed f. We can bound this term very nicely. The bound is exponential in n t squared. It's great. N is large, right? N is the size of our sample, so it grows down. The power of this exponential probability goes down very, very quickly. Perfect. Okay. Now we have to think about what do we do for many f. So this is all. This argument was for 1f. Normally, before, what we did is we took the union bound over the class, but this class is now infinite. We can take the union bound over infinite classes. Otherwise, we'll be summing up, this probabilities infinitely many times. Too bad. So what we do instead is we will apply VC theory. We'll apply Sauer-Shelach inequality that says that since the VC class is VC dimension is finite, the cardinality of the class cannot be too large. So that's the next step. Before we can do this, we need to, the VC theory, the Sauer-Shelach lemma, applies only for finite domains, and our domain is not finite. So we need to make a restriction. So we're working toward application of Sauer-Shelach lemma, so we make a restriction. This expression right here. If we think about it, let's just think. It depends only on what f is doing on the sample. And the sample has n, cardinality n. So we can drop everything else and pretend that our function class, our functions are just functions on the sample, on the n-point set. And that's what will allow us to apply Sauer-Shelach lemma. Yeah, understood? No big deal here, but just saying that this expression so this expression, the one that we want to bound, is determined by the values of f on the n-point set, which is the sample. So we can automatically replace the class f, which are functions on the real line, or possibly infinite subsets, infinite set, by its restriction onto the onto here. Let's call this f sub n, for example. So these are all functions that takes value on the sample. How do I carefully write this? Just need to restrict. So restriction x1 through xn, something like that, right? where function is an f. So we just consider this function on the sample only and forget everything else. Now the functions, now we can apply Sauer-Shelach lemma. Well, Sauer-Shelach lemma. I'll remind you what it is. So this was the main result in the VC theory that says that any class on an n-point domain with VC dimension D has this cardinality. That's literally the Sauer-Shelach lemma. If f takes values on an n-point set, then it can't be larger than this. And we did this simple computation based on Stirling's expansion, maybe that this is smaller than. Let me just cheat a little bit. I think this will be en to the d, but let's say it's less than n to the d. Okay, good. Okay, this proof has a little non-trivial step. So if I just want to make sure that everything is clear, everything is okay now. We're like 5 lines away from the end of this proof. So if anything is unclear now, let me know.
So for me, maybe I don't just understand it, but this lemma requires a fixed set of points, and we have
Sauer-Shelach.
Yeah, Sauer-Shelach. We have expectation, and as I understand, we want to like uniformly apply it for what we have under the expectation.
Mm-hmm. Yeah. That's a good question actually. So what we have is this. Let me kind of backtrack the steps of the proof. We started by taking this expectation, everything is fine, we're still here. But when we apply symmetrization lemma, after that, we've condition on xi's, we treat them as fixed, and now we are applying expectation, this expected value, over the signs epsilon I only. So now the sample is fixed for us. And what happens in the rest will just prove, we'll continue the proof for the fixed xi. Okay. Then in the very, very last step, we say, well, because this expectation is bounded for any for fixed xi, for any xi, it must be true that it is for anything. In the very end, we take the further expectation with respect to xi and done. That will be the very last step. But inside here, we treat everything as fixed, except the signs. Yeah. But
regarding that.
Yeah, let me let out my dog from here. Sorry.
Okay.
Yeah. Get out of here, little dog. Working from home.
The dog is like, I have a question.
Anyway, yeah, someone. Any other questions?
Yeah, so before the fixation event of like this xi, we have expectation both with respect to epsilon i's and xi's. Yeah.
Mm-hmm. Yes.
Okay, and then we fix them, and we have expectation only with respect to epsilon i's.
Only with respect to epsilon i's. Yes. Yeah. To okay. Maybe. To,
yeah,
mm-hmm.
Yeah. Mm-hmm.
Yes, if any. Okay. Maybe to make it a little bit more transparent. Okay, a little bit more transparent. I would write it something like this: expected value with respect to epsilon, expected value with respect to x, like this. And what we're doing now in the body of the proof, we're just bounding this for a fixed x. If we can bound it for a fixed x by some number, then we just, of course, the expected value with respect to x will be also bounded by the same number. So that's what we're doing. Yeah, so these are good questions. Very good to clarify that. Anything else? Any other questions? Good, good. Let's go on. So what we did, we apply again. So we want to bound this. Perfect. We apply symmetrization. We fixed xi. Now all randomness is with the signs. Because signs are so simple, random variables, plus or minus ones, we can apply Höfding's inequality, for example, to bound this for fixed f. And we get a super nice bound, exponential in n, very, very nice bound for each fixed f in the class. Now, how do we unfix f? We need to replace f by a finite class. And Sauer-Shelach lemma is doing that. So we first restrict the functions on the class. We get endpoints domain. We apply Sauer-Shelach lemma, and this is our bound on the cardinality of the class. Now our class is finite. It's actually very small. Quantitatively, we know what it is. Perfect. At this point, we just apply the union bound, and everything checks. So union bound. To pass from this inequality for one f to this inequality for all f. So if I take supremum with respect to all f, there is this 2 that we lost on the way, but that's okay. So 1 over f, 2 over f, some epsilon I f of xi is greater than t is bounded by what? Okay, let's now think. What does it mean the supremum or maximum? It's a finite class, so maximum is greater than something. It means that there is a function, there is some f for which this expression is greater. There exists an f means that we take the union bound over all f. Right? Probability of the union bound is smaller than the sum of probabilities. So it's smaller than this many terms times the probability for 1. And probability for 1 is this. 2x minus nt squared over 2. Good. So we take this bound and make a union bound over it. We pay the cardinality of Fn. Oh, wonderful. So we know what cardinality of n is, n to the d times this. So okay, let me actually do it simpler. It is less than n to the d, and we bring this inside the exponent. 2x of n to the d, so it's d log n minus nt squared over 2. Okay, so that dictates the choice of t for us. We want this to be small. So we want this term to dominate. So we want this to be something like minus nt squared over 4, for example. That happens for any t that's larger than, let's think. So we need to equate these two. So that's t will be okay. Let's say 10 root d log n over n. I think I was lazy to compute the exact constant, but it doesn't matter. 10, for example, is okay. So let's call this t0. Good, that's already a very good inequality. To pass from this to expectation, we can apply, finally, to pass to the expected value, we can apply the integral identity that says that for any random variable z, positive random variable z, this is how you compute the expected value in terms of the tails. We applied it many times before. And we will apply this specifically for the z. This will be our z. expected value of z is integral from 0 to infinity. We actually can break it into two parts, this integral. We only have this bound for large t greater than t0. So before t0, we don't know anything. After t0, we know pretty good estimate. So that's why I'm breaking this into two parts. Before, we don't know anything, so this must be less than 1, for example. Probability is always less than 1. So I get the first bound is t0, and the second integral is this. 2 minus t and t squared over 4 dt. And now it's a little exercise to compute this, but I guess you'd believe that this goes down so fast that this is going to be small, actually. So this is like twice t0, for example. Even at the very beginning, if it starts at t0, it's already e to the minus n t0 squared, which is much less than t0. So yeah, you need a little check this carefully, but the last term will be small, and that's it. So we proved the theorem. We proved that the expected value of z, which is this, is bounded by twice t0, which is this. That's what we wanted to do. That's it. Good. Any questions? We proved this was a nice proof, combining symmetrization and concentration. So everything that you learned in this class, or most of what's your symmetrization and concentration inequalities like Hoeffding's, and symmetrization, of course, and VC dimension and Sauer-Schellach lemma and integrals, everything kind of works together very nicely. And we get this beautiful result. The uniform law of large numbers. Any questions before we go to examples? Okay, now our class will be lighter. We'll just have examples. First example is for the half-lines. Let's apply this uniform law of large numbers to the class of these functions, minus infinity to a in R. So these functions are very simple. It's just, this is our real line, and this is our function. Takes values 1 or 0. That's what f looks like in this class. We already decided a couple classes ago that VC dimension is 1 for this class. And so what's uniform law of large numbers? Let's just literally apply uniform law of large numbers. Let's see what this means for this class. Uniform law of large numbers says that the empirical mean is close to the true mean. Okay, what's that? Expected value of the indicator that x, indicator of what? That x is less than a, right? What is this? Expected value of the indicator is always probability. Exactly, Danny. It's probability. It's just a probability that x is less than a. Which is the cumulative distribution function. The cumulative distribution function. What is it in Ukrainian? It's cumulative distribution. Do you remember?
Функція розподілу.
Функція розподілу. Так. So this will be the функція розподілу of x, this cumulative distribution function of x. And this, by the same reasoning, this is 1 over n. Now f of xi can be either 1 or 0, so the sum just counts how many xi's are less than a. Divide this by n. It's just a fraction of the sample that is less than a. And that we can call fn of a, or the empirical or sample CDF, the empiryczna funkcja rozpodziału of x. So the uniform law of large numbers then says that expected value of the supremum over the class, which is parameterized by a, fn of a minus f of a is less than this. And this is a sup norm. When you take the maximum overall, the maximum of the function is called the sup norm. So what we get is we derived Glivenko-Cantelli theorem, classical result in probability theory that says that for any distribution whatsoever, any random variable x, the cumulative distribution function of x can be uniformly estimated from a single sample, from a sample of n points, a sample of n copies of x, so which means that fn minus f in the sup norm is less than c log n over n. This is what it would look like if you made an experiment, and you can do this on the computer, make an experiment with any distribution. And this is my sample, maybe. Like this. The true CDF, the CDF of x may look like this. This is f of x. And the empirical CDF will look like this. It just jumps. This makes this, too bad. I have to jump higher, I guess. And this will be fn of x. So it will snug tightly, it will follow very tightly the true CDF all over the place, right? Not just at one point, but everywhere. This is fantastic because this means that not just one quantile, but all quantiles of any distribution can be determined, can be estimated from the same sample. You don't have to resample the data. Did you guys know this theorem in statistics? I don't know. Yeah, okay, good.
Yeah,
good. Then great. So then you probably know that the Glivenko-Cantelli can be proved without VC dimension. There is a direct proof of it. It's not very hard. The point of making this connection to Glivenko-Cantelli is that our argument now, the uniform of large numbers, is much more general. It applies not only in one dimension, for which you know Glivenko-Cantelli, but for example, in 2 dimensions. And in 2 dimensions, we could use, so another example, we can use, for example, the axis-aligned rectangles. Axis-aligned rectangles. So things like this. Mathematically, it's just AB times CD. Yeah. And still this argument, the same argument applies with the VC dimension of axis-aligned rectangles. We already talked about this as 4 parameters, so it's not surprising. ABCD. And so the argument applies, and you have Glivenko-Cantelli now over rectangles. And that will be much harder to prove directly, although possible. But for circles, for example, it was pretty impossible to get a direct proof of Glivenko-Cantelli, or for ellipses, for example. And this general argument applies just without any change, very smoothly. So let's illustrate this. For, let's say, X has uniform distribution over 0, 1 squared, for example. Uniform distribution over a square, the unit square. And we take a sample. Lots of points. Square. Then expected value. Then, okay, let's apply uniform law of large numbers. What does it say? Expected value of f of x is the area of a rectangle. Expected value of f of x is the area of the rectangle. R here. Clear, right? Because it's uniformly distributed. Then expected value of x is a probability. Let me write this down. It's a probability that x is in R and x is uniformly distributed. So this must be just the area R. And the empirical expectation or sample mean is again just how many points are in R over n. So the fraction of the points that fall in the rectangle. So the uniform law of large numbers simply says that the area, the number of points in each rectangle, the fraction of the points in any rectangle is very close to the area of the rectangle, uniformly over all possible rectangles. We proved that actually in this class using a direct approach without VC dimension, without anything. So this partially recovers a result we proved on the discrepancy. That was the key word. But that time when we proved that result on discrepancy, it was pretty partial to the rectangles. We could not have proved it for circles, for example. And now we can just rerun this argument for circles. Circles also have VC dimension that's finite. It's actually 3, or ellipses, and so it works for any shape. So we have discrepancy results. Uniform law of large numbers allows us to get results for any VC class with finite dimension. So ellipses, circles, triangles, anything, any shapes, and any distribution. Okay, good. Any questions? Okay, maybe I will be over the time by 5 minutes. I need like 6-7 minutes. Would that be okay? Because I want to finish this thing today. So sorry about this. Maybe we'll need another 7 minutes, but it will be worth it. We're going back to machine learning. Thank you. Back to machine learning. Okay, so now all of what we've studied was motivated by the machine learning. So let's recall the setup, the empirical risk minimization method. empirical risk minimization algorithm from lecture 35. This was a setup of a very general setup of mathematical foundations of machine learning, where we want to predict y from x. Let's say y will be the diagnosis of a patient, 0, 1, and let's say x are the symptoms. So we'd like to predict the diagnosis from the symptoms, for instance. For this, we would like to we compute the risk. I'll explain what this is again. So H is a hypothesis. It's a function. Let's say H is a linear function. For each linear function, we make a linear regression. So we take a linear function, we compare it with y, with the diagnosis, and then we measure the discrepancy. We measure the error with some loss function. For example, L of would be just the square function, t minus s squared, and we take expectation. So it's just the average squared error. This is a risk, also called the test error. And we would ideally like to minimize the risk. So we would like to find the function that minimizes the risk over all allowed functions. This is a hypothesis class. So in advance, we choose the hypothesis class. For example, the class of all linear functions. We will be running linear regression. That's our H. We quantify the error. The error measures how well does our hypothesis, does this particular linear function fits the data, and we minimize this risk. So we fit as tightly as possible. We cannot do this though. What we can do, well, we can't do this because we can't take expectations over the entire population. What we can do is we can only compute the empirical risk by averaging on the sample only. So instead of taking the expectation, I'm taking the average on the sample. That we can compute for each H. And then we minimize it. That we can also do, at least theoretically. So this is ERM. This empirical risk, also called the training error. And this is a true risk and the test error. This algorithm is called ERM, empirical. It's a meta algorithm. It's not a specific algorithm of how we minimize. We minimize using optimization, but this is a meta algorithm called empirical risk minimization. So we redefine our set, our hypothesis class, let's say the class of linear functions. For each linear function H, we compute how well it fits the data. That's empirical risk or training error. So we train the algorithm. And then we choose the best one, the one that minimizes the risk. So this is the training stage. By doing this, we get Hn star. That's our oracle. It's a function that can predict the diagnosis. Okay, remember that? Okay, perfect. This is the setup of ERM, of basic setup of machine learning. What we proved about this is a generalization bound. We would like to make sure that the algorithm generalizes well. And the simple bound is like this. This is what we want. This is the test error. What is the risk of, how well does our oracle perform on the new sample? So it's smaller than R of H star. This is absolutely the best possible you can do. Plus to supremum H and H. Not repeat this proof. Sorry, this was a little like 4-step proof here. This. The problem, so okay, so this was Rn of H. What's Rn of H? Let's write this down. 1 over n, from 1 to n, the loss yi minus expected value of L, H of xy. I'm literally rewriting the definitions here. And when you look at this, that thing is just the uniform law of large numbers. It's exactly what we did in the uniform law of large numbers. So we can apply this. We can call this thing f of xi, let's say. Apply uniform law of large numbers, and we get the theorem. The fundamental theorem is called VC generalization bound. That says that if H is a Boolean class with finite VC dimension, then the test error, which is the ultimate measure of performance of the algorithm, is bounded by absolutely the best possible theoretically in this class. This is as if I knew everything about the diagnosis and I was like Superman who knows how to classify things, plus this term d log n over n. So if we ignore log n for a moment, if we want this to be very, very small, let's say, this is okay if n is greater than, I think, d log d or something like this, d, which is, I think d log d would be okay. But let's ignore log for a moment. So greater than c prime d. So the ultimate message that this theorem is sending us is that the algorithm generalizes well. So we always have good generalization if the sample size, from the sample size n, which is approximately on the same scale as the VC dimension of the class, up to log. So that's the ultimate message. If you think about it, VC dimension is like the number of parameters that parameterize the class. And we're saying that you take this class of this many, or like 11 parameters, how much training data you need to train it? Well, about the same as the number of parameters. Yeah, not very surprising, but that's that's now a mathematical result. And there are two sources of errors here. This one is how well the chosen model, the hypothesis class H, describes the data. For example, it could be that the diagnosis is not linear at all. It could be that the real dependence on the sickness on the symptoms is not a linear function. It may be quite complex. It may be polynomial. And by you choosing the linear class, you make a very oversimplifying assumptions. And therefore, whatever you do, if you can even train the best algorithm, it will not work just because you're assuming it's linear, right? So that's what this is saying. And this is saying that And this is a generalization. This says that assuming that you did everything well, can we make an algorithm that generalizes, not just memorizes the diagnosis of the training patients, but generalizes it well to other patients? And this is how we do this. If this is a number of parameters, this is a complexity of the class of the hypothesis class, which is like the VC dimension of the number of parameters. And this is the error, the risk, or the test error, the ultimate performance of the algorithm. It does something like this. The risk first is very large when the complexity is of the class is very small. If you have just very few parameters, then it's too simple model. This number will be very large. And that may be small. So this is where this, okay. This is what we'll see. So R of H star is large. That was as bad here. Then it goes down. And at this end of the scale, we run into the opposite problem, where this generalization error is too large. This one is too large. We're increasing D here. And so these two terms, they are in competition with each other. There is a trade-off between the simplicity of the model and the generalization. This is in statistics, this is called bias variance or variance bias trade-off. So somewhere here, we would need to equate. Someone here, there's a sweet spot where the model is not oversimplistic, so it actually captures the complexity of the data, but also it's not too complicated, so that we're not just memorizing things. Okay. We'll keep doing this. On Monday, the one thing last thing to mention is that the log factor can be removed. From all of the results that we have seen, the log factor can be removed. We'll not go into the details of that, but by the log factor, I mean this log factor. It's not super important, but just should know it. Good. So that was a success story in mathematical understanding of machine learning that kind of explains how learning works mathematically. Good. Any questions?
Yeah, I have a question.
Yes, Dennis.
How have we applied uniform law of large numbers to VC generalization bound? We take supremum over H, but there is Y. Y doesn't.
Yeah. I was hoping someone will catch it. You're right. Yeah, we can't really. Yeah, not literally, at least. Yes, thank you for noticing this. Let me repeat this concern of Denise, that when we're applying uniform law of large numbers, and let me show this uniform law of large numbers again. Yeah, this is the bound that it works. Uniform law of large numbers applies to functions f of xi. Right? And now, in addition to xi, we also have this label. So it's not just a function of xi, but also of the label yi. Yeah, so we can't really literally apply it like that. Unfortunately, and so what you can do and what is done in machine learning is you go back to the proof and manually allow this also to depend on something else, on yi. And then you just redo this proof and you see nothing happens, actually. Nothing changes here. So all of these things in here could depend on yi and this on y and so on and so forth. and this one yi, and this one yi, and this one yi. And then when we condition on xi on the data, we condition on xi and yi, and nothing happens after. Then everything becomes fixed. So the proof goes without change, but it needs to be amended. It needs to be adapted to these labels. You're absolutely right.
Can we consider it like a random vector, or like merge them together and say that it's just one, but it's have a more complicated structure?
I guess. I don't know. Maybe the thing is that problem is that yi sits outside h. If it was like h of xi yi, it would be okay. Then we can just couple them together. But it's h of xi yi, and then there's this function. Yeah. I don't know. Maybe. Yeah, the simplest fix is just to insert yi's there and check that nothing changes. It doesn't hurt the proof. Maybe you can do that. Any other questions? Good. Okay. This was quite a class, and it was quite a big chapter in our study in applications of pretty much all we knew about machine learning. And now next week, I had a hard decision to make. What can we do in 3 classes? The 2 options that I had were either do something more applied, which is privacy and security of the data, or to do something more kind of tool, like foundational. It was a hard decision. And the problem, so I'm partial to privacy and security. This is what I do, and the negative thing about this is that you will not have transferable tools. Like, you will learn about privacy and security as we know it right now, but it will change in 5 years probably, and the tools that you will learn in the 3 classes will not be transferable. That they're just, there's not too deep math that I know how to present there. So I think it will be actually more in the tools, in the stochastic processes tools that are applicable in the more general context. But I would like to hear from you. Let me stop recording now.